Hello and welcome to our Engineering Go-Kart Challenge. We are going to try to figure out how we can use our knowledge of forces to create a safe go-kart. So far in this unit, we've learned about force, we've learned about motion, we've learned about acceleration, velocity. And so we're going to take all of what we've learned and apply it to creating a safe go-kart. If you have some of your own materials, you are welcome to do this on your own. You can make a Lego car, you can use another type of car that you have around, and as well as some of the other supplies. If you don't have the supplies, no worries, I'm going to do it for you on this video. All right, so let's talk about what we're going to be doing. We want to define the engineering problem. So remember back in Unit 0, we did a little engineering project. So we're going to review engineering and what that means. We're going to develop our criteria and restraints. For the problem, we're going to design a model together, and then we're going to test our different models and modify designs according to the results. So here we go. Engineering challenge, designing safe go-karts. If you have not yet read the engineering worksheet, please go and complete this assignment first. So what you're going to do is read and highlight this document. It is 4 pages, and it just talks about our engineering problem and what it means to define an engineering problem and come up with solutions. So please do that first before moving on to this video. Please pause if you need to do that. Let's go over a little bit about it. A go-kart experiences many different forces during a race. The force of the engine propels it forward. The friction of the track slows it down. For riders, the most dangerous force involves collisions. Go-karts must have safety features to withstand those forces. So what do you think some safety features of go-karts are? We're going to think about it. You can kind of use this video as well. This guy is obviously wearing a helmet. Looks like there's some like rubbering around the go-kart. And then the track also has tires on the outside. So the rubber to rubber contact during a collision will help them not get hurt. So we're going to talk about a little bit more about some safety features in our go-kart in a little bit. So just think about that in the back of your head. What are some safety features of go-karts and what we could use to apply that to our model? So we're not going to be working in groups. You can kind of ignore that, but you are, think about yourself as an engineering team. We're going to define our engineering problem. We're going to develop possible solutions, and then we're going to optimize our design, which means we might need to change some things depending on our outcome. So here is our problem. You and your team will create a go-kart model that can withstand different amounts of force. So our model is going to look a little bit different, but here's this model here. Each of these pieces of tape is going to represent a different amount of force. So we're going to use the same size ball. We're going to roll it down the ramp at different levels of the ramp. So if you think back to our Hot Wheels experiment, that the farther up our ramp, the more acceleration we're going to get, right? So this is just going to be a little bit. This is going to be a little bit more and a little bit more. And here's our model, our go-kart model, that we're going to add some stuff to it. And then we have a test tube filled with water. So we want to design a go-kart that makes it so the very little water spills out and it stays upright in our go-kart design. So we're going to need to do something to keep that upright. So on our worksheet, your worksheet looks like this. So it tells you a little bit about what we're going to do and some of the materials that we're going to have. You can kind of ignore that because you don't really need that unless you want to collect some of these and do it on your own. So the first step is going to be to build our go-kart. We're going to use a beaker of water filled up in our test tube to test our go-kart, make sure that no water is spilling out. We're going to test it first from the small force line, and then we'll move up from there. So what you guys need to be doing is, first of all, we're going to fill out this criteria and constraints together. And then you're going to fill out these kind of pre-lab questions. And we're going to draw our model. And then we are going to fill out any data that we collect from our trials. All right. So if you need to get situated and get started, go ahead and pause this video. Otherwise, we're going to jump into criteria and constraints. So before we begin, let's decide what are the criteria and constraints we need to apply to our design. So what should the criteria for the design be? So our criteria, our main thing that we want is to make sure that our test tube does not spill out the water. So we want to make sure our test tube is upright and stays in the right place. So that's our first criteria, okay? And then also that the model can't break, right? We don't want to break our model. So those are two things that we're going to put in here. So we can add a text box and we can add criteria is we want to, that's really hard to read. Keep. We want to keep our test tube up, and we want to not break our model. So those are some of the goals. Now our constraints, what are our limits in this? So we are going to have limited supplies, and it can't be taller than 18 centimeters and it can't be wider than 18 centimeters. So it just has to fit on our track basically. So we're going to put those in, and unfortunately I don't have a way to weigh it. So this does say no more than 85 grams. So we'll kind of guesstimate on that. So it needs to be 18 centimeters, less than 18 centimeters high. Wide and high. And less than 85 grams. And we also have limited materials. All right. So I want you to take a minute, pause this video, and you're going to answer questions 2, 3, and 4, kind of applying what you already know to this model. When you're done with that, you can go ahead and come back. Oh, I'm sorry, you need to answer 2, 3, 4, 5, and 6. So you're going to make a prediction. What do you think will happen when the ball collides with the cart? You're going to apply Newton's laws. You're going to think about the motion of the car. So you're going to answer 2, 3, 4, 5, and 6. So go ahead and pause this video, take a few minutes, answer those questions, and then when you are ready, we are going to draw our go-kart. All right, so you should have answered the questions. I'm going to show you guys our materials for this activity. Over here, we have our go-kart. This is also called a Hall's carriage. So you can see it's got wheels on the bottom and it's got a space inside there. That's where we're going to be putting our test tube of water. It's not filled yet, but here's where our test tube will go. And then here are the materials that we get to use to help our go-kart. So we're using this. We've got 2 cotton balls that we can use. We've got a rubber band that we can use. We have 10 of these centimeter cubes. Each of these are a gram. So remember, one of our constraints is it can't be over 85 grams. So we know that these are each a gram. And these are probably a gram or less. And then we also can have a piece of paper. And then we can also use some tape to hold some stuff. Can't tape down the test tube, unfortunately, but we can tape some of these things. So we can rip and tear any of these different items and use them to create our model. So I want you to think about, if you had these materials, what might you create with your model? You're welcome to either draw what you would want to do in the box, or you can end up drawing what we decide to do in ours. So for our first trial, I'm actually going to just leave it totally blank, fill this up with water, and send the ball down, and we'll see what happens. All right, here is my ramp setup. So I've got my house carriage with my 10 milliliters of water on my ramp. Here is my small, medium, and large amounts of force. And here is my 2-inch ball that I will be using for all of our trials. So first one, and also I have it marked, so I'm going to always start my car at this blue line, which is 2 inches from my ramp. So line that up. We're going to start with the small with nothing in here, and then we're going to modify our design. So we'll see how much water spills out and how far this goes. 3, 2, 1. Whoa, definitely went off the ramp and spilled all of my water. So we are going to measure this, see how much that is, and then we will modify our design by creating something else. So I want you to think about if you were doing this in person right now. So this went 17.5 inches. So what could we do to this model to make it so that it can withstand some force? So I want you to think about that and then watch as I create something to test it out with. Okay, my model is complete. So I went ahead and put some paper on there to kind of make like a point and kind of protect the test tube. So hopefully the ball will hit that instead. And then I also put the blocks down underneath my cotton balls, and then I spread my cotton balls out and put them on top of the blocks so that hopefully this will stay in there. So let's give it a try. I gotta fill my test tube back up, and we'll try it out with our small one. I didn't record any information from the first one because we want to do it against, let's see, perform our test on your model against medium. Okay, and then the large. So I'm going to start recording data using my finished model because the first one was so challenging and it didn't go very far. So I'm going to set this up. Here we go. All right, I've got my start of my car because I had to move it back a little bit because of my point on the blue line. And I'm going to drop this and we'll see how far it goes and how much water spills out. 3, 2, 1. Whoa, it didn't move very far. That was good. Okay, so we're going to gather some data. So no water spilled, so that's awesome. And my test tube stayed upright. And it only went about 1/2 inch, which is awesome. So we're going to do one more trial. And then we'll fill in our data table. 1, 2, 3. Oh, that time it did knock it over, but no water came out. So that's good. So think about how we might modify this for our next trial on the medium. So this one about 1.5 inches. So let's go back to our data table and we will fill it in. So some of this we can't necessarily fill out because I don't know the mass, so we can just cross this off. But the distance it moved is, the first trial was 0.5. This was in inches, so we're actually going to need to convert that in a second. And then this was 1.5 inches. No water, 0, 0, observations, what will we change? So the test tube, we can just write like the test tube did fall over. In that one, what are we gonna change? Like, I'm thinking about maybe we could somehow maybe make it so that the test tube secures it a little bit more. We do have this rubber band, so maybe we could add that into our model because I didn't actually use my rubber band in the model. Oh, and we need to do the height and length of my model. So it can't be more than, what was it, 18 centimeters. So, oh, it's exactly 18 centimeters, so that's good. And it's 8 centimeters wide at the widest part. So come back here. Our length was 18. Our height is 8. And our width is 8. So we can copy and paste this here. And next we're going to convert these to centimeters. So I guess next time I'll measure on the centimeter line. So 1/2 inch in centimeters is like, yeah, it's about 2. So we're going to change this to 2 centimeters. And this is 1.5 inches. We're just guessing, we're rounding 4 centimeters. All right, so we're going to change my model a little bit. So I think that I'm going to somehow use my rubber band to secure my test tube a little bit. Because it did fall over, and we're going to do the medium this next time. So let's see how I don't know how to put this on here. I wonder if we could just put it around the test tube. How about that? What if we did that? Let's see if it would hold it. Ooh, it's kind of like a seat belt, huh? All right, let's test it out. We're going to do medium next. All right, here's my model on the line. Let's see how far we're going to go. We're all the way up to the medium line. 3, 2, 1. Oh, that actually went pretty good and nothing spilled. Let's get my ruler here. Okay, let's see. First trial in centimeters, so we don't have to convert it, is 16. So we'll try the second one. Bum, bum, bum. 3, 2, 1. Ooh. All right, 16 and 13. All right, let's go back to our data table. Say hi to our sleeping dog. So we're going to copy and paste because I didn't do anything different to the size of my model. So it's still 18 by 8. And this time it went 16 centimeters. And then it went 13 centimeters. This is the same, so we can copy that. 0 here, 0 here. I don't know. I don't think we need to change anything. So the seatbelt worked well. If you have ideas, you can definitely put them in here. I'm gonna say not changing anything. I do have, the only thing I have left is some paper, a little bit of paper left. So we could, you know, attach something else to just make it like way more, or, you know, a little bit, maybe air resistance. Maybe we should do that, is put a little bit on the back so that it doesn't travel as far, so that it kind of like stops a little bit. Let's do that. Might as well, we're experimenting. So I have this amount of paper left, but I actually can't go any farther out. So what I'm gonna do is I'm gonna tape it here. Okay, here's my new model. And I think this will also help protect the test tube as well. So I only added height to it, which we had some leverage in that, or some ability to do that, because it was only 8 centimeters and it can be actually 18 centimeters. So here's my cool model. Hopefully it will help with some like air resistance. So here we go. We're gonna go on the largest amount of force. Here we go. 3, 2, 1. Ooh. No spilling, so that's great. We're gonna measure this, so keep these numbers in your head. 23.5. We'll do one more trial, and then we will add our observations. And 23.5 and 29.5. 23 and 29. Let's remember those numbers, Mrs. Powell. And we're going to measure this because now I added some height to it, so it's a little bit different in the height. It is at its tallest point 12. All right, 23, 29, 12. All right. 23.5. Centimeters, always include your units. And 29.5. And nothing, and nothing. And our length was 18 by, width was still 8 by, our height, well, our new height was 12. So I'm just gonna say nothing, it worked great. So I think that little air resistance thing was good. We put that on there to help protect everything, so that's great. Awesome. So I want you to go back through, make sure that you have filled out all of your data table with our information. You're welcome to cross these out since we don't have any way to measure our mass. And you should draw a picture either of a model that you would like to test or our model that we used, or you can take a picture from the video, screenshot it and put it in there. That works too. We measured this, so you can put that in your drawing as well. And make sure you've answered all of these questions and you'll be good to go. Thanks for joining us on our engineering go-kart model.